Thanks everybody for being here. I'm really glad to be back at Stanford where I did my PhD and really talking about a body of work that has been spanning at least 10 years, but has really kind of taken off in a new direction that I'm really excited to cover throughout the course of the talk today. And it's really going to be going over this idea of trying to unlock the concept of autonomous surgical robots. I want to start with this idea of what are robots actually, leveraged for. And I think one perspective that you can take is that it is really to meet this growing need for skilled labor, right? And this need is happening across all kinds of industries, of which healthcare is one that, is both significantly impacted, but also industry that we absolutely are intrinsically tied to, every one of us. If we look at the shortage of healthcare workers in this country alone, we're looking at currently numbers of tens of thousands of surgeons that are not trained, are not sufficiently trained in terms of meeting the needs of the patient population. Simultaneously, we're seeing shortages of hundreds of thousands of nurses necessary to meet the demands of the healthcare population. And so, with this observation, robots are actually a very, very strong opportunity to kind of come in and provide significant value. They have some very nice properties, such as they don't get tired. I mean, they need charging, of course, but they don't get tired. They're available 24/7. They have precision that often can go beyond human capability. We talk about CAD and CAM precisions from the machinist kind of point of view in sub-millimeter ranges, and we could, in certain platforms, get that type of precision as well in robotics. The very interesting thing about robotics as well as a platform technology for scaling skilled labor is that in the healthcare practice today, we have this notion of one physician or one nurse training side by side with another physician or nurse, right? And this is a very linear kind of increase in making that skilled labor group grow. However, for robotics, these can be conducted kind of on a fleet-wide update basis, just like autonomous vehicles. I'm not sure how many people drive Teslas in this room, but of course, you can have an example today where overnight you'll get a new software update and the system will have acquired some sort of new autonomous skill. Finally, this idea of programmable expertise is really interesting, and how many people have gone into healthcare settings and wondering, well, what is the quality of care I'm getting in this setting versus another setting or another individual? In this case, you can program, uniformity of expertise across these platforms. I want to give an idea of where current paradigms of medical robotics are today. This is a Da Vinci surgical system. It is a teleoperated surgical robot that moves inside, is placed, it has tools that go inside your body, and the surgeon operates these tools using a joystick console, as shown here, and the tools inside your body move basically directly proportional to the movement of the surgeon. This robot has been around for well over 25, if not 30 years at this point. And if we look at where the landscape of surgical robotics today, it's really exploded, right? And this is just a snapshot of all the surgical robotics out there. There are a significantly higher number of robots that I couldn't put on the page. But the point I want to make is that all of these robots are teleoperated today. They lack inherent, they have zero inherent skill. The skill is coming from the surgeon, and it does make surgeons more precise and less tired, But what it doesn't do is it doesn't help us address the population crisis issue. It does not help us do more surgery. And in fact, when you're doing robotic surgery, oftentimes the surgical team that's required to perform the procedure requires more personnel than if you were to do it without a robot. Okay. Now, if you look on the other side, where there is autonomous robots being deployed, it's manufacturing, right? And in manufacturing, it's all rigid pre-programmed motions. They operate in a very structured environment. They require extensive setup and human oversight, and but they do excel at speed, precision, and repeatability. This is autonomy, but in an unskilled way. So what if we try to merge the concepts of autonomy and surgical robotics? This concept is actually not new at all. If you can believe it, this is concepts that have been dating back many decades, both from things like Robodoc that was used for orthopedic surgery and doing small alignments for implants, to ASOP, which is a voice-controlled robot that holds a surgical camera for laparoscopic surgery, to methods from university labs that have looked at using what is very popular today, concepts of imitation learning or learning from demonstration to show things like autonomous suturing. Okay. So all of this has been kind of a progression of new techniques back in the day that have been kind of applied over and over to try to address this issue of surgical autonomy. And in certain cases, we've been able to show some successes. But if we look at where are we recently today in terms of general robot autonomy, we're looking at these ideas of large foundation models or vision language action models, which usually require large data sets, which is massive data collection at scale, or developing what's called world models, like simulations or generative models of the world that are trying to describe how the world evolves over time. And what we see in this space right now is a large variability between accuracy and success. And so there's a lot of tasks that are kind of shown that can be very successful at decent accuracies in the mid to high 90% range. But there's also many that are failing dramatically. And all of these foundation models have been developed in what I would say is relatively clean and controlled settings where stakes are low, the environment can be easily reset, and for the tasks in which the demonstrators are abundant. So people that can sit down at a console and just show a robot how to fold a piece of laundry. Almost anybody can do that. But surgical robotics has that issue of none of those properties really exist for surgery. So that you have scarce data, the setting cannot be controlled, right? The setting cannot be easily reset. When you're doing a surgery, you can't kind of roll back time normally. Safety is absolutely critical, right? So few demonstrators, right? We already talked about the lack of surgeons, right? So there's even fewer demonstrators, and there's very low incentives for them to be sitting and doing demonstrations for a robot learner. Data collection in these situations is basically at the lowest priority, right? You're usually trying to address the patient and not to address the machine learning algorithm. And finally, world models right now have no concrete path to maturity. Given that there is a limited data, that data is protected behind, and reasonably so, behind privacy laws, right? And so how else can we approach autonomy? And so we can kind of look back at these, what I would say is kind of the foundational pillars of autonomous robots. And I would say that there's four that I would categorize as, one is perception, seeing kind of and perceiving the world and feeling the world. Second one is modeling and simulation. So understanding rough models of how things move, the general physics of the world at a small scale. Planning, understanding how to make decisions given that you know how the world evolves, and then control, actually executing those actions in a precise way. And all together, in various types of methods, we can bring these all together to get what we call embodied intelligence and autonomy. So at my lab at UC San Diego, we have been playing around with these four pillars quite a lot and trying to build up the technology to make surgical autonomy possible. And we've looked at a large range of different areas of autonomous suturing to assistance to deformable modeling and probing to very specific robot applications like biopsy and cancer. And I think what we've learned and what I feel like I've learned over the time is that at least one very viable path to unlocking autonomous intelligent robots in surgery is a structured path of building context awareness, moving towards incorporating multiple knowledge cues to kind of build on this knowledge to be a lifelong learner, and then finding common embodiments so that we can deploy it at a larger scale. So I want to kind of cover these ideas during this talk. So for achieving context awareness, what I'm really talking about is perception. Okay, so robot autonomy, in my opinion, can only be as good as its perception and its ability to recognize and understand the world. And only recently have we been able to get techniques very much, on the backbone of large data collection and foundational models to segment the world, identify, localize, and track targets. These are just two examples of the state of the art. And I'm sure that these will change within the next 6 months to something, even more powerful as the field progresses in computer vision. One thing I will say, though, is that surgical robotics is one of the hardest environments to work in for these perception tasks. Because oftentimes, when you're trying to understand a surgical environment, you have typically a very narrow field of view. You don't have context understanding globally. You have bad or no depth measurements. Usually you have either a single camera to understand in 2D what the space is like, but you have to infer depth from things like shadows and even understanding of like the anatomy that is being shown to you. So this is a lot of prior knowledge you need to have built up over time. Or in the other case, you have cameras that are stereo cameras. So you have two cameras that can do perception, stereo perception, but the baseline between the two eyes of the camera are so tight that you have very poor depth perception. Okay. You also, like I said, have specular reflections from fluids, blood, and there's smoke. When you're cutting through tissue, you're always kind of cutting through the scene with large instruments. And so it's always occluding your view. Everything is deformable. Sometimes it's hard to find an anchor point in the scene to know where things are static. And like I said, there's insufficient data to train modern neural models. And all of this is wrapped around the fact that whatever we learn, oftentimes we want millimeter precision. Okay. So how can we kind of break this down? Because this is a very challenging problem. And I will say we have spent all of the last 10 to 11 years I've been at UCSD just continuously working on this problem. And it can be broken down into several categories. Here is like the kind of four main ones, which is precise robot proprioception. That is the idea that as a robot, it has to know exactly where its hands are or its instruments are in space. Precise object localization. It has to know exactly where objects are in space relative to those instruments, right? 3D scene reconstruction, understanding the background of what it's interacting with, and especially in surgery, the background actually, it is a continuous kind of gradient from foreground to background, right? And so understanding 3D scene reconstruction and then scene fusion so that you, even despite the fact that you have a very narrow point of view, over time, as the camera moves around, you get a better sense of where you are in space. So we have done a lot of work in this area across surgical tool tracking, things like needle tracking, even suture thread tracking, for the explicit purpose of being able to very precisely get our robot instruments to grab objects in space. And we have also done, the third and fourth tasks of 3D scene reconstruction and fusion, which is really about reconstructing an entirely deformable environment. I wanted to spend a little bit of time on this because reconstructing a deformable scene is really important, not only from the perspective of being able to track where anatomy is as you manipulate it and move it around, and that's obviously important when you're doing something like excising a tumor, and you want to be able to make sure you're cutting with you have enough margin around the tumor as you cut and release it, so that you don't miss any lesion. But it's also important from the perspective of physics understanding. And so if we start with this technology that we had developed over many years to get deformable reconstruction from cameras of the scene, how can we kind of move that into a useful set of information to inform how do we do cutting and dissection? Okay, so if we go from vision and understanding of the scene to then instruct a robot how to cut, we need something in the between, and that is our model of physics. Okay, so what is absolutely necessary in this scenario is this understanding of the physics and mechanics of deforming tissue. So this idea is generally coined as digital twinning, and there's many techniques to do digital twinning. One technique that we were very excited about when we started was this method that was developed in computer graphics called position-based dynamics. And the idea of position-based dynamics was that you would simulate a deformable scene using particles, and you would run the particle interactions using a set of constraints that define how those particles would either bounce off each other or were constrained to each other. And the most important aspect of this was, number one, it could run faster than real time. And number two, it could satisfy position constraints exactly. So the first one I'll explain. If you have a simulator that can run faster than real time, then that means that you can simulate many possibilities, and kind of evaluate all possibilities of interaction with a tissue without actually interacting with it and waiting for a long time to figure out what the consequences are. So at the end of the day, you can close the loop on that and create a model-based controller that is very standard in classical robot control theory. So that is a very, very useful, and actually it's like a property that's absolutely necessary to apply those techniques. The second property of position-based dynamics was that we could take what we observed from the cameras, which generated this topological surface map, and we could force in one shot the simulator to match that. And that means that we don't have to do many, many iterations to get the matching to occur, and therefore it keeps that faster than real-time simulation from slowing down. So one of the things that we immediately found out was that if you go into a surgical type of environment and you recreate the environment from scratch, and then you immediately try to simulate it, because you're recreating the digital twin from just a surface image, you have to guess what is happening under the surface. And so right when the model tries to move the tissue in simulation, the simulation won't match real life. And so what we can do is, to correct for this behavior, we can use something called differentiable rendering. In a differentiable rendering, the idea is that we can both correct for we can take observations that are streaming in from a camera, and we can look at how those observations match up to the simulation. We can get a loss between the observations of the simulation and the camera image, and then we can backpropagate that loss to find how the simulator should change to make it match the real life. And in this case, what needs to be changed in the simulator is the mechanics properties of those tissues, as well as things like if the camera moved. Now, what we can see if we do that is that we can get the simulator to continuously match the observations coming from streaming video, and you can actually get a significant decrease in the amount of prediction error from your model before you do this iterative correction to after. And the difference is from several millimeters, 5 millimeters, down to sub 2 millimeter error accuracy. So this is for topological surfaces. Surfaces that are kind of mesh-like and topological in that nature. But we can also do it for things like rope-like objects. So this is taking an image of a rope and having a initialization of a simulator of that rope, pulling on the rope and understanding and learning the physics properties of that rope, especially its elasticity and viscoelasticity. You can imagine that this is applied in surgery to things like manipulating vessels and understanding the stiffness of those vessels, which is, of course, important for safety. We can do it for fluids as well. Fluids is just the extreme end of a soft body, right? And this is just an example of us looking at a video of chocolate milk being poured, and we're trying to estimate the viscosity of that chocolate milk. Now, of course, how does that relate to surgery? Well, we were very interested in hemorrhage control. And so when you see hemorrhaging happening, there's going to be a flow of blood, and it's going to start pooling. And what we were very interested in was to use a very quick understanding of the properties of that fluid to use closed-loop control to suction up the fluid as fast as possible. And so if we define a problem like that, it becomes an optimal control problem. And so we basically did model predictive control on this, where the model itself was this physics simulation. And then another kind of a thing that was very important to us was to uncover where connections are occurring. One of the hallmarks of surgery is that you're going to be dissecting through tissue, and you have to find where the tissue is connected. And one of the ways that we found that tissues could show that they were connected was when we pulled on it, we could see that the texture from the side we're pulling on at some point would have a sharp discontinuity in terms of translation. And so when we see that sharp discontinuity, that shows us that there is a connection in those locations. That's shown on the left-hand side in the purple. What we can do as well is to wrap this up in a Bayesian inferencing framework where not only do we have a guess of where the connections are, but we can attribute uncertainty as to where we think those connections are. And once you have a measure of uncertainty, you can incorporate that into a safety-aware control approach. And this is an example, at least in simulation, of how a robot autonomously would wrap a safety-aware controller around tugging on tissue to find out where things are connected before cutting. So in this case, the simulation of moving around this connected tissue is where the robot effector doesn't know that it's kind of connected on the red regions. And as it's moving around, it reveals those red regions are connected, and it will try to maximize the amount of information gained about other regions while making sure it's below some energy threshold, which is basically the tearing energy. And so given all of this, you can imagine that you've found a place where it's connected. Now it's time to cut. And so here's the example of us doing this type of procedure. I should have mentioned that all of these videos are of butcher shop meats. Probably should mention that ahead of time. But this is all on the bench type of work. So this is an example of our robot learning how to basically peel back tissue to expose the region of cutting for a secondary cutting arm to come in. And this is all autonomous based on model predictive control methods. Now, one of the things that is what is called like an emergent property in modern foundation models from robotics is this idea of recovery. And so, if you query, a foundation model today and it fails at a certain task, oftentimes people will show you that the policy will go back in and try again, right? Which is really great as an emergent property, but it's also completely uncontrolled in the sense that there is no actually guarantee that the robot will come in and try again. It's relatively random chance, at least like currently, right? But if you have an explicit model about where things, if you have an explicit model about what's happening in the environment and you've tied it to physics, you can query in that model whether it's failed or not, and then you can go in and you can be targeted and basically have surgical precision, for lack of a better word, of where to attack next and perform the procedure so that you complete the task. So one of these cases is where you're trying to cut through a piece of tissue and you have failed the cut. And if you look at using a model like this real-to-sim digital twinning framework and applying this continuous iterative matching routine to it, you can see that we can model where our cuts were effective and where they were not, and we can then go in and specifically cut those regions out, all in an automatic fashion. And so we can, this is an example of one of our autonomous routines cutting through this chicken. Yeah. Now, all of these are techniques that we've built up from the vision and the modeling and planning and control side. Basically, this toolbox, right, that we can put together for developing autonomous surgery. And by advancing these tools, we can improve the capabilities of these tools individually, and we can strengthen their reliability over time. And by assembling these tools in different configurations, we can broaden the capabilities of what we can automate while explicitly retaining explainability, which is extremely important in automating robotic surgery, where you have to be able to say, what is my robot doing? Is it going to be safe? And making sure that you as the supervisory individual is in control at all times, and it's not really the robot. So that's great, but everything I've showed you really has been piece by piece engineered together, and so every single task you have to hand engineer. And so would there be a better way to scale this over time? And so given a set of behaviors or policies, we want to find a good way to sequence them and combine them in a way that can be learned autonomously, and also in a way that can be learned in which new skills can be added over time. And so this idea is called lifelong learning. And it's still a very early field of research, and there is still a great deal to kind of explore here. One approach that my lab has been looking at is this idea of combining all of these kind of learned or engineered behaviors into a neural network that kind of glues them together. And so we call this knowledge-grounded reinforcement learning. And in this case, we have basically knowledge modules, as you can see in the green. And those knowledge modules contain the actual behavior of a small set of behaviors, and those behaviors could be very different. So some behaviors could be a robot camera that's moving around to scan something, or it could be a robot tool coming in and doing a cut, picking up objects, transferring objects from hands, many different kinds of behaviors that you can incorporate. And then the idea here is that using a very sparse kind of neural network architecture, where there is a little bit of weighting that's used to glue these knowledge modules together, you can create a framework where through reinforcement learning it learns by itself how these knowledge modules should be combined so that you can get a longer sequence of tasks done. So, for example, you have a knowledge set that you learned. In this case, we learned it using reinforcement learning in a simple simulated environment. We specifically looked at a task that was part of what's called the fundamentals of laparoscopic surgery, which is like an exam, basically, that laparoscopic surgeons have to take to prove that they are able to do the laparoscopic surgery effectively. And so these are things like picking up and grasping suture needles, moving blocks from pegboards from peg to peg, transferring objects between hands, and so on and so forth. So we can learn that using reinforcement learning. We can deploy them in real life and show that they are effective. Going from from the simulator to the real world, and then using the same kind of approach, we can show that it can learn to sequence the set of steps for doing multi-throw needle, multi-throw suturing. So with this kind of ability, it enables, I think a very interesting framework for building autonomy. But one thing that I've recognized we struggle with is that everything we've shown has been on this Da Vinci platform. Okay, and there's all these kinds of robots out there. And does this mean that we have to do the same thing for every single robot? Is there a best way to scale the usefulness of robot autonomy for healthcare when the robots are so diverse? And so, of course, recently, as everybody knows, there has been a very significant interest in humanoid platforms. Okay, and so back in about a year and a half ago, all of these humanoid platforms were coming out, and they were doing backflips and kung fu, a lot of things that didn't really speak to me about like how is this forwarding our society in a meaningful way. And of course, there was interest in their use in home care, although a lot of it was also in the use of their use in manufacturing, but not a single video or instance of anybody talking about its use in the healthcare system. So what we did was that we went out and we deployed one of these humanoid robots through mostly teleoperation. I'll get to exactly how much teleoperation later, but through mostly teleoperation in as many hospital settings as we could. And so this is what that project led to. This robot we named Sergi. Sergi is a humanoid robot with humanoid five-fingered hands. We specifically looked at common procedures that you would see, and especially in emergency scenarios, where we could justify the use, having a robot present to do a procedure when there wasn't a physician present had significant value and had a lot of, it was easy to justify. Some examples of tasks that are actually challenging, for non-skilled individuals to perform. This is an example, of intubation. You have obviously only a few minutes to get intubated before you suffocate and die. And so if you're in a situation where you can either trust a robot to try to do it autonomously or in teleoperated, or just, not have that, then I'm sure you would take the robot option. So here are just examples of what we were able to do through the Sergi platform. And I think what this is really getting towards is that there is a real value proposition for humanoid robots in a healthcare setting. Because if we think about the surgical robot I showed, the intuitive system, right now each system is over $3 million, okay? And you think there's very few hospitals, even in the United States, that can afford more than 1 or 2 Da Vinci systems. And to think about the remote communities that have limited access and capital and resources. And that is only for laparoscopic surgery, right? You can also think about scenarios where you have, surgical teams where a surgeon is working side by side with another surgeon, and this is actually more common than just having one surgeon operating in an operating room. You're usually working in pairs. If you're in an environment where you do not have enough surgeons, then you are actually taking somebody that's skilled, that could be treating somebody else, and putting them in a scenario where they're doing very, relatively limited skill assistive tasks, like holding a camera or retracting tissue and holding it back so that the primary surgeon can get a good view, right? And you can think about circulating nurses, you can think about scrub nurses handing off instruments, you can think about ultrasound techs. All of these applications, there's really not that much justification for having another robot and another robot and another robot, right? That a hospital would have to purchase and get approvals for to run through the entire pipeline so that they have sufficient coverage of all these application areas. But of course, humanoid robots with enough skill can do this. So we look at ideas of remote surgeon avatars, autonomous surgical assistants, and autonomous nursing and technicians. Okay. In the remote surgery aspect, we have been playing around with what it looks like to do teleoperation of a humanoid robot with laparoscopic tools. And this is just an evaluation of where are we in terms of this versus a Da Vinci robot versus somebody manually controlling the tools. And what we observe is that if you manually control the tools, that does require a lot of skill because when you're doing laparoscopic surgery inside a body with manual tools, all of your motions are flipped inside out and the axes are all inverted. And you're kind of working at a very different scale. But with robotics, you can change the scale, you can invert the axes just in software. So by doing this, even on the surgery platform, we can show it is better than a lot of people had an easier time doing it with humanoid than with manual tools. And we, of course, could not expect to, and we did not reach the level of a Da Vinci system, but that's okay because the Da Vinci system has been engineered over 25 to 30 years, right, to be perfect for laparoscopic surgery. But I think the point here is that the humanoid robot is, at least in this case, an interesting platform to keep looking into for those type of tasks. But beyond those tasks, one of the things that the video showed was all these diverse instruments that were being held and interacted with. And this is where the autonomy comes in. Because what we found was that it was nearly impossible to teleoperate a robot hand. And what I mean by teleoperate a robot hand would be we tried using cameras to look at our hands, and then we tried to have the robot hand match the hands of the that was seen in the camera and try to pick up objects and instruments and try to interact with it. They kept falling out of the hand, and we often squeezed too tight, and things like that. Everything you could think of would happen. And so, and the reason for this is because even though they look the same, like robot hands and human hands, they might look the same, but they're not the same in many ways. Number one, robot hands have a reduced number of degrees of freedom. You have size mismatches. Most of these robot hands are much bigger than you think and much bigger than human hands. I mean, like basketball player size hands. And what's really, really important, and it's going to be a really long road to development, is that they have limited sensing. And so on the right-hand side of this figure is one of the hands we use, and the red portions are where there's tactile sensors. Okay, so in these red regions is where you can get a sense of what the tactile forces are on your fingertips and in the middle phalangeal regions. But anywhere you touch outside of that, you have no tactile sensing. And you can imagine how difficult it would be to manipulate something like, a forceps, like a scissors, when you are lacking tactile sensing in those regions. So instead, one of the things that we could do is allow it to just figure out how to use these instruments on their own, no matter if it is similar to humans or not. And so we do that using reinforcement learning again. And so we massively parallelize robot arms learning to kind of hold and grasp onto existing instruments. Here are some examples of the behaviors of instruments that we were able to learn to use. What is especially difficult in all these cases, and why I'm showing these ones to you, is because these are what we call articulated tools. And so in one hand, you both have to have a very stable grasp of the object, but you also have to have the flexibility to move the hand to open and close or activate that object, right? And so you have tongs, you have pliers, forceps, and also a laparoscopic tool that's a trigger to it. And this is all done using reinforcement learning. Of course, we were still kind of on this desire to use learning from demonstration if we could, because if we could do that, we could save us a lot of computation time. Because reinforcement learning is definitely very computationally heavy. And what we quickly realized was that haptics, the feeling of touch, was actually very important. And it was not only the being able to recognize touch at the robot side, but able to deliver the feeling of touch back to the hand. And especially in the hospital setting, there's so many pieces of equipment that you're interacting with all kinds of buttons and knobs and plugs and wires, that you need very expressive types of haptics. And what we found was something as simple as pushing a button forward, like pushing it forward to hit a button. Nothing that we found online really found commercially could really do that. So you had gloves that you could put on that would constrain your fingers from closing, right? But if you push a button straight on, that has nothing to do with constraining your fingers from closing, right? And so that type of haptic feedback was just not available. So how could we, provide that back to the user? And so we went on this whole effort on building our own haptic glove. And so this is the first haptic glove that we know of that can do directional haptics on every finger. And so this idea is that you have linkage systems with multiple actuators on your hand that will push and pull your finger in many directions, so that things like pushing or sliding across the surface, you can actually get that tactile feedback, that force feedback back to your fingers. It is a pretty chunky system, of course, but one of the reasons why it's chunky, especially at the hand area, is because one of the design principles we wanted to ensure is that all of the system was actually at the hand, and there was not mechanical tethers to your wrist, and because that could cause ergonomic strain. So here's an example of my students operating the haptic glove. You can obviously use it also for simulations, as they're shown there, for doing virtual interactions where you can feel the forces. And this is just an example of the kinds of how the multi-directional forces are being generated from the linkage system. And so, we had strap this to our humanoid robot. We could push buttons and things like that, and really deliver a data collection approach as well as a teleoperation approach that was much more effective. So I talked about the use of these robots in hospital settings, but beyond hospitals, one area that I found was very underdeveloped was this idea of managing pain, and especially chronic wounds. So chronic wounds is a very significant problem, not only in North America but around the world, in terms of wounds that are healing slowly or will maybe never heal, and they constantly need bandages removed and changed. 2% of the population in North America have chronic wounds. And so this, especially for those who have mobility impairments, they need caregivers, to help them change out bandages and change out these dressings very frequently, often on a daily basis. And this is a massive toll to the patients, caregivers, and families. You can imagine that I already said that there's not enough nurses in the US. All of this usually rests, like the majority of this falls on the family members, right? And so you can imagine that in these cases, over time, the dignity of the patients are affected, and they absolutely are looking for solutions where they can independently live and have autonomous robots assist in these complex cases. So we started on this project, and we started bringing in all of our tools, from deformable modeling to doing optimization-based control. This is a case where we were teaching a robot how to peel off bandages with a notion that you would peel in a direction so it would minimize stretching of the skin and reduce pain. And then we further on went to looking at how do you manipulate tape and then tape back on new bandages. So the idea of dressing removal, preparing the tape, placing the tape down. And here are just some examples of, the tape video didn't work of it peeling the tape. But here are just some examples, recent examples of the robot trying to autonomously place the tape down with all of the vision haptic models that we had developed. And this is still early work. You can still see a little bit of shaky hand happening there. But I'm very hopeful that as we move this forward, that we're going to get these robots to solve a problem that is really impactful to our society. Another kind of fun thing is that none of these robot hands had fingernails. So we actually had to create our own 3D printed fingernail for our robot to peel the tape. All right. So, where do we go from here, right? I think I feel like in the years that we've been working on this project, these types of projects, there's been a lot of validation as to the approach of building vision systems, models that describe key areas of physical interaction with humans and their bodies, to kind of trying to scale in controlled and specific ways. And I think that we should keep pushing along this path. I think there's value in large foundation models and interacting with them and companies that are trying to push that forward. But as researchers in this area, I also feel like the more that we can build mathematical models, understand the physics behind the techniques that we want to deploy in robots, the more generalizable and adaptable they can become. And so there's still a lot of work to do. So all of these projects, every one of them has been motivated by and has been developed in close interaction with our clinical team, shown here. Many students have worked on these projects. One of the things I'm very proud of is also the student graduates who have now become faculty members at their own institutions, who are now developing medical robotics and moving them forward as well. Thank you for your attention. I am very happy to answer any questions.
Thank you very much. To your last sentence, I'm curious where you see the value of foundational models and where not. And in the foundational model development, whether, like right now, more and more companies are coming out, whether you see consolidation or trying to get all of that, they will have specific versions.
Yeah, so the question of where do foundation models go from here and how does that maybe integrate with what we're doing? At least that's how I interpret it. So because I do think that there is a integration stage here. We are using foundation models for vision, for segmentation. We're using foundation models for tracking. As these models get developed, and more generalizable, we very much are happy to take what is out there, if it's good enough, and integrate it in as like either the main method for one of those pillars that I mentioned, or a supplementary method. And this mixture of approaches, I think, leads to robustness. So you don't necessarily have to rely on either black box architectures fully, one way or the other. In terms of where foundation models will head and whether all these companies are going to eventually consolidate to rely on one model versus another, I don't know, to be completely honest. But I will say that we have so many problems in robotics, and they have such diversity that it would be hard to think that there's going to be one robot model that will work for everything. I think if you take surgery as an example, that is such a specific domain with very specific needs and very specific limitations of data and safety, that it would be a very, very long time before I can imagine a model that could, clean up your kitchen is the same model that could perform surgery on you. Yes.
Very, very interesting work here. So going back to the early part of your talk when you mentioned the visual difficulty of knowing what's going on underneath the surface, and I can understand why you focus on vision. You come from teleoperated robots and those that deliver a camera view to the surgeon. But as part of your work, I'm just wondering why you would it be useful to think of other modalities, so like acoustics, little ultrasound to look underneath the tissue in addition to the vision, and somehow integrate that. When you think of autonomous robots, don't necessarily need to be the same as what you would use if you're doing teleoperated.
Yeah, absolutely. So the use of things like ultrasound are ones that we've actually played with in the past, and I didn't show it here, but it is absolutely important to use whatever imaging modality you have. And like you said, a robot can not only interpret the images as humans generally could, especially if you look at the development in radiology today and how AI has kind of transformed that field, but it can accumulate, and juggle all of that knowledge in some ways much better than humans could. So spatial awareness as you're scanning an ultrasound probe, and incorporating that into understanding of the tissue geometry underneath. Yeah, ultrasound, yes, I think is a very, very exciting area. Just as a context, one way you would deploy ultrasound here is that there's ultrasound pickup probes. So what you do is that you drop a probe in that's an ultrasound scanner into the body, and one of those surgical tools will actually pick up the probe, and now you can scan it. So we've actually done work like that before.
Yeah, really interesting.
Yeah, thanks.
So when it comes to training data, as I understand, this is one of the primary bottlenecks right now. What would you say are some bottlenecks in general in when it comes to training data? Is it like the raw data? Is it labeled data? So
yeah, I mean, so of course, yeah, if you're getting data from basically the wild, right, then there's a challenge of what is useful data and what's not useful data. I mean, this is a really big question of what are the challenges, right? I would say more tied to what I talked about, one area that I think people are starting to clue into as being something that really needs a lot of work is capturing force data and tactile data, because so much of our interaction with the world depends on feeling the world. And so the challenge, and why probably this is not the first thing that everybody goes to, is not only do we have limited interfaces to feel the world, as I showed, we had to build our own, but we also have a material science problem here, because most tactile sensors today are very there's a lot of limitations in tactile sensing today, that they can, if they're sensitive, they can break easily, or they are not robust. And if they're robust, then they are very sparse in nature, and they're not very sensitive. So this kind of trade-off is a really difficult material science problem. And for that reason, At least I think it's going to be quite a long road ahead to solve it. But at the same time, I think we still need to forge ahead to incorporate whatever force and tactile data we do have and see how far we can get with what we have today. Yeah. Yes.
So speaking on the touching, you mentioned on the start of the presentation the tearing energy that you have. I'm very curious to see if that has anything to do with the foundation models and physics behind those foundation models that you talk about. So like the importance of these foundation models, the fact that they can give the raw understanding on this tearing energy?
Yeah, so in terms of tissue tearing and using that in closed loop, that was done using the local physics simulator in position-based dynamics. So this PBD simulator, you can get an energy metric out. And so it was not using any foundation model at all. Yeah, and how do we associate that physics model with like a boundary energy metric is from vision, because we can see how things are moving and we can associate it, the viscoelasticity that way. Yeah. Yeah.
I'm very curious about, I feel like you have to, it's not like a robot, it's not like a manufacturing robot that's doing this very repetitive work, right? So that's why it sounds like you have to create a very unique time and space for each task. And then, so this is a kind of, you often hear about the scalability, issues. So I also see this one is a combination of hardware, software. So just want to get a general sense about how much is about hardware, how much is about software, And I know it has to be embodied and it's really challenging. So just want to get a sense.
I mean, okay, so you're probably asking somebody that's pretty biased in this opinion of how much is hardware and how much is software. I started in mechanical engineering, so you're probably gonna guess my answer. But I think obviously, like software is absolutely critical in here. But I think having the right hardware having an effective piece of hardware. I mean, right is, I don't know if there's like always a right solution to everything, but something that's effective is important, because I don't think any amount of software can make a crummy robot achieve what it needs to achieve. So a lot of the robots we use in surgical robotics are designed very carefully to be inherently safe. They're back drivable. They have like very little like backlash, and so it doesn't jitter, and it's very smooth. So yeah, it's very, very well engineered from a mechanical side. Yeah, hardware side. Design is very important here. Yeah.
Preserving best tissue from tearing. It's a question that comes up a lot in sort of above the neck surgery. Have you looked at trying to set boundary conditions to avoid tearing tissue when you have instruments pushing on the surface?
Yes. So this is absolutely something we've been really interested in as well. So we look at it from a retraction standpoint. One of the things that I showed was a video of the tool that was pushing, like kind of revealing the next location to cut. That actually was incorporated in that was this metric of how much pull is too much, right? So that I'm stretching it too far. And so the same metric can be applied both to be, to inform, what is safe and unsafe to tear. Yeah, please.
One of the big problems in neurosurgery, particularly critical zone surgery, like brainstem, thalamus, sort of deep brain structures, is that we don't understand the degree to which we can manipulate the tissue before you produce a bad outcome. Are you aware of, or are you interested in work like that?
That's very interesting. Yeah, I mean, I'd love to talk after this about it, because I think I suppose you can kind of come at it from two perspectives, right? Like as a neurosurgeon yourself, I'm guessing. So you have built up prior knowledge about what visually you think is going to be like within safe regions, right, of manipulation. And I think we would have, like, I would probably approach it from the same angle. Like, how do we teach a robot to visually understand what is within safe regions? And then every time we enter into a new, like, patient, then we apply that prior knowledge, and we maybe adjust it for the patient, like the patient, like age or gender, well, whatever properties that might affect that. But I think we can look at it from a human training angle. That would be the way to go.
And there was that sort of that trend in the mental or cognitive demand between people's operation surgery and Da Vinci. Correct me if I'm wrong, were you using, so the teleoperation interface, you were still using the MTMs of the Da Vinci for both controlling the humanoid and the Da Vinci, and so was there any difference in the view that the teleoperators were getting?
No, so yeah, this is a great question. Yeah, so for that study, we're using the same user interface and we're using the same camera. So the difference here, it's a very interesting point because this is actually a big issue. So, and it's actually a big issue for Da Vinci, but they solved it, which is that in laparoscopic surgery, you often are in, like, you actually have to work in a pretty large workspace because you're at a fulcrum. You're entering in a fulcrum, and your hands have to kind of move around pretty far. And the problem was actually that we were constantly hitting the range of motion for our humanoid robot because the G1 robot is not actually that big. Like, that has that large of a wingspan, basically. And so we kept hitting these joint limits, and so people were taking longer for that reason. Yeah. And the intuitive system has kind of been designed to minimize that as much as possible.
But with the G1, you still had to program for the remote center of motion.
Yeah, everything like that was programmed in already. Great, thank you.